Sarah, Karina, and Daniel, and we're the Toyota team. Our industry mentors, Alex and Tan, could not be here today, but our lovely active lingering is with us. And we're the Toyota team. So, just a little bit of introduction of who we are. So, can I get a raise of hands? Who has seen a Toyota before? That's what I thought. Pretty much everybody has heard of or seen a Toyota before. So you probably are very well versed with what it is. But what you probably didn't know is that Toyota is the world's leader in hybrid vehicle sales. And in particular, they're very committed to electrification. For example, 2 years ago in 2021, Toyota announced a $70 billion investment in electrification. And perhaps more excitingly, this is from July 2023, Toyota has claimed to have a battery breakthrough that halves the size and cost of current solid-state batteries, but doubling the performance, which is pretty exciting to see. And this is why we're interested in this project. Specifically, we're interested in the battery of an electric vehicle. So measuring how a battery ages, it's not hard to see why this is important in an electric vehicle. It tells you more about when you need to change the battery or replace it, but it also tells you how much range you can go on a single charge. So there's two different methods to determine the cycle life of a battery. One is a data-driven method, and the other one is a physics-based model. A data-driven method essentially is you collect a bunch of data points about a battery and its charge policy, and you plug all of that into a machine learning model and have that figure out the trend for you. This has the advantage of being mechanism agnostic, which means that you don't really need to understand how the physical or the chemical processes of a battery work. However, a physics-based model has the advantage of incorporating this knowledge and potentially being a better model because you already have this prior knowledge of how the chemical process of a battery works. So our goal of this project is twofold. One, Severson et al. Wrote a paper 2 years ago. It was a very seminal study on using a data-driven approach to measure the cycle life of a battery. We aim to construct model architectures that improve upon their results. So that's our number one goal. Our number two goal is to incorporate physical information into this data-driven approach to form a hybrid model. So first what we did is that we recreated Severson et al.'s prior work as our baseline model. In particular, we used the same data as they did, which consists of 124 battery cells of varying lifetime, and they are charged where there's charge and discharge repeatedly until the end of life, and we call that a cycle. So we take these following measurements from each cycle. We take the discharge capacity, the voltage, the temperature, the internal resistance, amongst other features. We chose to list these 4 features here because it is well known in the literature that these 4 features have significant physical meaning into how a battery operates. But we've chosen these 2 bolded features here because those are the features that Severson et al. Chose, which Karina will now guide us through next.
Thank you, Nathan. So let's take a closer look at what this data actually looks like. First, we're just going to focus on one battery and one cycle. So a single charging and discharging of the battery. Here, the plot has time on the x-axis, and we're first going to look at the red curve, which represents voltage. So voltage increases from 2 volts to 3.6 volts during the charging portion, and then decreases back to 2 volts during discharging. At the same time, we have discharge capacity in blue. So discharge capacity is at 0 throughout the entire charging process, and then it increases to 1.1 amp hours during the discharging process. That's a lot of information to feed into a model, so for our purposes, we're just going to be looking at the discharging portion of the cycle based on the work of Severson et al. So we have these 2 metrics, and we can actually condense that into a single plot. So here we have voltage decreasing on the x-axis from 3.6 to 2, and we plot that against the discharge capacity on the y-axis. So we see the discharge capacity going from 0 to 1.1 in a sinusoidal shape. Again, that is just for one cycle, but we can also think about that curve being constructed for multiple cycles over the course of the battery's operation. So as the battery gets older, we can imagine the curves going from top to bottom. The curve actually sags, because for a given drop in voltage, as the battery is older, you get less discharge capacity. This is especially apparent for batteries with low lifetimes, because the battery degrades faster. You can observe the same phenomenon in a battery with a higher cycle lifetime, but the trend is less apparent. You notice that the curve still sags, but it's less noticeable. So based on the shape of the curves over time, you can actually distinguish between batteries with high and low lifetimes. But there are lots of cycles you could choose from. So for the paper we look at, they focus on cycles 100 and 10. So you fix those two cycles, and you can imagine cycle 10 as representing one of the dark curves near the top with little sagging, and cycle 100 is one of the lighter curves near the bottom with a lot of sagging. If you take the difference between those two curves across the entire voltage range, you get a difference plot. Here you notice that the difference near high voltages is near zero, because at the beginning of the discharging process, all the batteries are going to start at zero discharge capacity. But the difference becomes far more apparent during the discharging process, which is why we have this big dip. Now finally, we can actually make this plot for all of the batteries in our data set. Here, the darker curves represent batteries with longer lifetimes, and the lighter curves represent batteries with shorter lifetimes. Notice that the shorter-lived batteries have large dips, whereas the longer-lived batteries have very small dips. So this is something we can also use to distinguish between batteries, and is a more condensed form of the data. Specifically, we can take summary features from the curves, such as the variance, the minimum, the mean, the skew, the kurtosis. Combine those other features from the battery to feed into a regression model for cycle life prediction, which Sarah is going to talk about next.
So now we have extracted all the features that we need to implement our predictive model. So the diagram on the left shows the complete flow of our model implementation. So we have this big raw data set of charges and discharges that we use to extract insightful features, and as explained by Karina, and then we divided them into different model features. So as suggested in the paper, there were 3 model features, each consisting of different subsets of feature, namely as variance model feature, which is here. It consists of one feature related to charge. Then we have discharge model feature, which consists of 6 features related to discharge curves. And then we have full model feature, which consists of all 9 features. After doing this subset of feature, we did the train test split on these features. So instead of doing a conventional train test split where you feed in 80% of your data into the training phase and 20% into the testing, we divided our features into 3 parts, which is training, primary, and secondary. And this is what makes our problem even more challenging, because the batteries in the secondary test have different charging policies than what we are feeding into the training phase. So now we have to come up with a model that is more robust to varying charging policies. So for that reason, we trained elastic net model. Elastic net model is a mathematical model. It's a linear regression framework which offers you the advantage of regularization. Those of you who don't know regularization helps you prevent overfitting in your model. But in order to get a robust elastic net model, we need to feed in the right set of hyperparameters. And to tune our hyperparameters, we employ the technique of randomized search CB, which selects the best sets of hyperparameter in a particular context of data. So, after training ElasticNet, these are the results that we got. The first row shows the results from base paper, and the second row, which is highlighted, it shows the results from our model. So the evaluation metric that we use to evaluate these results is RMSE, which is known as root mean squared error. It is basically, it quantifies the average difference between the actual value and the predicted value. If I keep it simple, it is, if the RMSE it's low, it's good. If it's high, it's bad. So remember this throughout the whole presentation. So as you can see here, our scores are pretty much close to base results, but we still need improvement, particularly in secondary test, because the RMSE is very high, which means that there is a significant difference between the actual value and the predicted value. So here is our second approach in building the predictive model. So previously we were feeding in the statistical feature. Now we are using those features to formulate the time series out of those features. So in the prior work, we noticed that they were computing a single point of difference of charge between cycle number 100 and cycle number 10. But after analyzing the cycles, we analyzed that there were few points in cycle that have unusual behavior than other cycle points. And one point of difference is not enough to capture the complete information. So we calculated the difference of all consecutive cycle points starting with index 3 and going on till index 100. So now we have 98 points in our time series, and we are using this as an input for implementing our predictive model. So this is basically the visualization of how we have computed the difference. If you can see the darker shades, the darker lines here shows that these batteries have good cycle life, and the lighter shades, the white ones, show that they have low battery life. Now Daniel will explain why and how we use autoencoder to handle the time series.
Thank you. So now that we decided we're going to use a completely different kind of data, it makes sense that we're going to explore different kind of models, right? So the first thing that we tried was to adapt the model that we used to recreate the Severson et al. Results to just take in these full time series and then predict the cycle life. This did not work very well, and that is because now the input data is very, very high dimensional. Whenever you have input data that is very high dimensional, all the underlying relationships become pretty complicated. So it's hard to then perform any kind of machine learning problem, such the regression problem that we do here. We decided, therefore, that the first operation that we need to perform is dimensionality reduction. So dimensionality reduction aims to find a lower dimensional representation, such like a low dimension manifold that all the data points lie around, which then will simplify all the underlying relationships and then will make the further problems, such as the cycle life regression, easier for us to perform. A model that is pretty good at this is shown here, which is the autoencoder model. And the autoencoder works by firstly running an encoder phase. The encoder phase takes this large input X and runs it through a series of classic feed-forward layers. These are these output data points that are lower and lower in dimension up until that layer in the middle, which is the encoding. The encoding ideally will fully summarize all the information that was originally in the input. How do we make sure that this will be the case? We run it through the decoder stage. The decoder stage upsamples this encoding in a similar manner as the encoder downsampled it and obtains X hat, which is ideally identical to X. Because if we were able to reconstruct the input from the original encoding, that means that the encoding encapsulates all the original relevant information. We train this by trying to minimize the error between X and X hat. And after that, we discard all the decoder layer, and we're left with the encodings that you see in the green layer. So far, so good. Autoencoders have been shown to perform very well before on dimensionality reduction. But there is a slight problem here. These encodings are now very, very general. The autoencoders just find some kind of low-dimensional representation that just encapsulates the information. But we're not sure if this information is actually what we want for prediction, if it's going to be relevant for what we're going to do next. To tackle this problem, we designed a second generation of this model, which is the two-head autoencoder. And to the best of our knowledge, this has not been done before, so this is one of the big novelties in our project. It does a similar job as before, so we still have the decoder layer, the decoder head that takes the encoding Z in the middle and aims to reconstruct the original input. But at the same time, we are using that elastic net head that you see there, which is an orientative prediction head. This is basically a linear regression that is applied to the encoding in the middle. And it basically checks that whatever we have now is actually relevant for prediction. So now the training is going to be done jointly on these two heads. We're still going to have the original error between X and X hat that checks that whatever encoding we have encapsulates all the information. But at the same time, we're going to use the orientative prediction, the elastic net head, to also enforce more specificity into the model, to enforce that whatever features we ended up with in the encoding are features that are good for prediction later on. So a few more details on how we trained this large model. We came up with a custom loss function that is made out of 3 terms. We have the classic autoencoder loss as before, which looks like this. It's the mean squared error between the input X and the output X hat, averaged over a batch size B, and multiplied with a weight lambda decoding. There is a second term, the new one in our case, which is the prediction loss, the orientative prediction loss. Again, it's a mean squared error averaged over a batch size B and weighted with a certain weight lambda prediction. The reason why we have those powers there is probably less interesting than you would think. It's simply because initially we took the logarithms of all the input values, and we also took the logarithms of the ground truth labels, and we're using that instead of the original values. And that's just because the relationships between them are simpler, and the models have an easier time to work with that. But then to have a correct loss function, of course, we need to exponentiate them back. The third term is just the regularization term for the orientative prediction head. We combine all of these three into our custom loss function, and this is basically what we're using to train that big model. As it is the case with all custom loss functions, especially with those with many terms, there is a big challenge in tuning these weights lambda. And that is because each of these three terms, they might have different orders of magnitude initially. They might evolve differently during training, so maybe one of them will go down faster than the other. One of them might converge faster than the other. And also they address different parts of the model, so maybe we will want to favor one head over the other later in the training. So it took us quite a lot of experimenting to find out the right combination of these weights lambda. How did we do it? Initially, we just set them to be equal, and then we ran a coarse training over the whole model. You can see here an initial performance. So on the left side, that is the performance of the encoder-decoder. You can see we have the decoded input on the y-axis and the original input on the x-axis. And so the closer the points are to the x equals y line, the better. We see that the performance is not too bad. And the same goes for the right-hand side plot, which is the orientative prediction performance. Again, in a similar way, the points lie quite closely to the x equals y line, which means that our model does a good job in the beginning. But if we later want to fine-tune one of the heads, and especially the orientative prediction head, because this is the end goal of this model, to produce encodings that will later be relevant for prediction, then we can run another stage of training with different kind of training hyperparameters, such as a lower learning rate and a different set of weights lambda, and then we can independently tune either of these two heads. And that's basically it for the two-head autoencoder. The next step is to, again, discard the decoder head and the orientative prediction head, because that was not the final prediction that we're making. We're taking those encodings, and then we feed them to the real prediction models, which are the SVR, the support vector regression, and then a self-attention layer. Sarah and Karina will tell you about these in a minute. So, Sarah?
Thank you, Daniel. So before moving forward with support vector regression, let me give you a quick recap of what we have done so far. So the first approach was feature-based approach. We were feeding in the statistical features into the model. The second was the time series approach, where we calculated the time series from those features and feed those features into the model. Now the third approach is collapsing the dimensions of the time series and feeding that into our model. So from 98 points, we have collapsed that into 16 points using the autoencoder. Now the next challenge is which features do we need to actually feed into our model? We have the collapsed dimensions of all the features, but we cannot feed them all into the model. We need to handpick the best features that will work best and contribute the most to our model. So for this reason, we calculated the Pearson coefficient correlation between our target variable and the features. So this heat map shows the correlation calculated between every other entity, but I want you all to focus on the first column of the heat map, which shows the correlation of the target variable with all the features. And if we keep the threshold, let's say 0.5 and above, so we can see that delta Q log bars, delta Q min, and delta T log bar have the strongest correlation with the target variable. By strong correlation, I mean it can be positive or negative. By positive correlation, it means that when one entity increases, the other also increases. By negative correlation, I mean that when one entity decreases, the other also increases. So if we can see that delta Q log bar has a correlation of 0.78 minus 0.78, which means it's negatively correlated, delta Q min have a correlation of 0.6, which is positively correlated, and delta T log bar have a correlation of minus 0.52, which is a negative correlation. So we handpick these three features and we feed them into our SPR model. After training the SPR model, these are the results that we received out of our model. So as I told you before, that the lower score means that the score is good. And as you can see that the test score has significantly improved from what we have achieved previously. But we still need to improve our results on the secondary test. So for this reason, we use self-attention to improve our model, which Karina will explain.
Thank you, Sarah. So first of all, what exactly is self-attention? There are two big types. The first is known as narcissism, and the second type you might have heard about if you know about transformers, which are a form of deep learning model. Self-attention is the crux of a transformer because it's able to learn the relative importance between tokens in a sequence. So for a traditional example, you might think of a sequence as being a sentence, and the tokens are the words in that sentence. For our case, we're looking at a time series as our sequence, and we're trying to see how the different features in the time series relate to one another for prediction purposes. Here's a visual representation. So we're going to use the sentence example because that's a little easier to understand. So say we have an input of n words, each of length d in. You take each of those words and project it into a query vector, a key vector, and a value vector. You can think of the query vector as being each token's signature call, and the key vector as being its signature response, and the value as relating to the prediction in some sort of way. Next, you take each pairwise combination of tokens, token 1 and token 2, and you take the dot product of token 1's query vector and token 2's key vector. And that tells you something about how those two tokens relate to one another. If you do those for all of the pairs, you end up getting a matrix. And if you take the softmax of the matrix along each row, you normalize it, and that gives you what we call the attention matrix. So the attention matrix gives you all the information about how different tokens in the sequence relate to one another. You can use that for prediction purposes by taking the product of that and the value vectors you calculated earlier. And if you want to collapse the dimensionality further, you pass it through some more linear layers. And that ends up just giving you an output y, which is just a number in our case. And we would imagine that to be the cycle lifetime of a battery. OK, so next I'm going to pass it off to Nathan, who's going to talk about the results.
Yeah, thanks. So this is our performance comparison of the 2-hat autoencoder and SVR and our 2-hat autoencoder plus narcissism. So in our 2-hat autoencoder and SVR, notice we have a train of 63 cycles, a test of 90 cycles, and a secondary test of 290 cycles. And this is a plot of the predicted versus true labels we have here. So note that the closer the points are to this black line, the better they are. And now here we have our 2-hat autoencoder and self-attention. Notice that we have a train error of 59, a test of 84, and a secondary test of 254 cycles. So notice that this is 254 is a pretty significant improvement upon our 290 number from earlier, and this is the plot of predicted versus true. So putting everything into context, our 2-hat autoencoder and self-attention gives us a train of 59 cycles, a primary test error of 84 cycles, and a secondary test of 254 cycles. And notice that this number here, the 84, is a pretty significant improvement upon our baseline result of 122, while keeping secondary tests pretty standard. And lastly, for our future directions, one future direction that we can consider is to refine our transformer performance. We notice that our errors after our autoencoder layer is already pretty good, and transformer only provides a marginal decrease in error. So using different self-attention methods in our self-attention layer can potentially be a strategy. Second, like Daniel said, we've managed to incorporate our autoencoder and elastic net into a single loss function. A similar thing can probably be done with self-attention and putting that into our autoencoder / elastic net model. And lastly, we can continue to incorporate physics-based knowledge. Currently, what we have here is that we've used physics to select the features that we want, but nothing really much has been said about the physical processes or the chemical processes of a battery. So trying to use that and putting that into our model can also be potentially really useful as well. So that concludes our presentation. Do we have any questions?